Good morning, Physics 11s. It's online lesson number 9, Law of Conservation of Energy. Hope you're having a good time. Sunshine's back out and get out and play. But we've got to do a little bit of work first. This should be review for a lot of you, but for some of you it might be new or feel like new. There are 3 main types of energy, and I know this is a gross simplification, but 3 main types. Potential energy, we call it PE in my class anyway. Kinetic energy, KE, and heat. They're all measured in joules. So they are units in joules, and that has a symbol, capital J. Without too much theoretical background, just let you know that potential energy, PE, is a whole bunch of different types. There could be potential energy stored in a battery in the form of chemical, could be in your body, stored in your muscles as chemical energy. Those are types of potential energy. The type of energy that we're looking at for potential energy in physics, at least in Physics 11, is gravitational potential energy. So gravitational potential energy is a potential energy that you have from being higher up or lower down. So depending on where you are in your height above the ground, you have the potential to damage yourself, for instance. That potential energy has the formula mass times gravity times height. Kinetic energy always has the formula 1/2 times mass times velocity squared, and heat comes from friction, and we'll talk about some examples of that later, but it's also measured in joules, and in fact potential energy and kinetic energy can turn into heat, but eventually everything does turn into heat. It doesn't have a formula. All of these energies are connected by the law of conservation of energy. You've already learned about the law of conservation of momentum in lesson 8, and you've learned about the law of conservation of mass in chemistry. This is the law of conservation of energy. Initial total energy equals final total energy. So potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final plus heat. If any friction is there and it produces heat, it goes on the right-hand side. I want to take a look at an example of the law of conservation of energy with a situation that you've probably been in before. Cultus Lake has a free-fall water slide. It's called the Free Fall, and it's fairly tall. There's one at Disney World, though, which is a lot taller, and it's called Summit Plummet. So just imagine you up here, pond down here, and what I want to do is use the law of conservation of energy to determine what your speed would be down at the bottom. Just to give you some background, at Cultus Lake, the freefall water slide has a height of about 22 meters or so. At Disney World, Summit Plummet has a height of 36.6 meters. And that would translate into a speed, they say, of about 100 kilometers an hour at the bottom of the water slide. Pretty impressive. So we'll see. We'll use the law of conservation of energy to see if that really is the case. In this water slide, you're stopped at the top until the lifeguard gives you a little push, and you have the most stored energy you will have on this ride. You've got all potential energy for the entire ride up at the top. So at the very top, you've got no speed, no kinetic energy, but you've got all potential energy. Somewhere in the middle, you start having about the same potential energy as kinetic. And at the bottom, you have all kinetic energy and no potential energy because you have no height left at the bottom. So basically what's happening in this ride is you're changing potential energy to kinetic energy, and your maximum kinetic energy is at the bottom, where all of your potential energy is turned into kinetic. In this pond right here, you lose all of your kinetic energy to heat. There's all sorts of friction with you and the water. Some people even lose their bathing suits because of that friction. And it brings you to a stop at the end. So all of the energy you had up here, all the potential, eventually just turns into heat, and it heats up that water in the pond. There are other types of friction that you encounter on the water slide as well. Could be air friction when your speed picks up. Could be just you bumping against the sides of the water slide. But we're going to look at a simplest example right now where there is no friction, so no heat is produced. Filling in some details, the height of the water slide at Summit Plummet is 36.6 meters. Let's say this is you, and let's say, for instance, your mass is 65.3 meters, or 65.3 kilograms. And let's say in this example there's no friction, so there's no heat. It's the simplest example, because that term right here ends up becoming zero. And just making it a usable form of the law of conservation of energy to put numbers in anyway. Just replace the potential energy with mgh and kinetic energy with 1/2 mv squared, and then heat is heat. So mgh initial plus 1/2 mv initial squared equals mgh final plus 1/2 mv final squared plus heat. And all we need to do is just put numbers in. So putting the numbers in, I get 65.3 times G is 9.8 on Earth. H initial started out at 36.6. So initial is up here, final is down here, just before the pond. The height, 36.6. The initial speed is 0. So 1/2 times m times 0 is 0. So the whole term is 0. At the bottom, we've lost all the height. There's 0 height. So if that's 0, mass times gravity times 0 is 0. Plus 1/2 times the mass, 65.3, times the speed we're trying to find, plus the heat. There's no heat because there's no friction. So this term is 0 in this example too. And of course the big question here is, what is your speed at the bottom of the water slide? We're trying to find VF, which is the speed of you at the bottom of the water slide. And let's calculate. Here we go. And the next step of the calculation, up a little bit, I end up getting 23,422 on this side, rounded up to 5 digits, and that equals 32.65 times V final squared. I want just V final squared on this side, so I have to divide this entire side by 32.65, and I have to do the same thing over here. So I'll do that. Finishing up the calculation, we end up getting a final speed of u on the water slide at the bottom, just before you hit the water, the big water pond, of 26.78 meters per second, which is pretty remarkable. In fact, your speed is so remarkable, 26.78 meters per second, it's faster than you can run. The fastest human is around 10 meters per second. And that's a lot faster. We'll find out what it is in kilometers per hour in just a sec. And we get a speed of 96.42 kilometers per hour, which is about your speed on the freeway. At Summit Plummet, we actually did get some speeds on our radar gun just over 100 kilometers per hour, and it probably had something to do with people pushing off, and they've got water flowing down the water slide too, and it picks up speed, and it gives you some of its energy as well, kinetic energy, so you pick up speed a little bit there as well. Their radar gun was also getting speeds fairly regularly, over 100 kilometers per hour. That is a bathing suit ripper at the end for sure. We'll revisit this question right now as a part 2, this time with friction. So we'll just say that, for example, in this problem, we created 5,550 joules of heat through friction. So it could have been air friction, you knocking the sides of the slide as you fell, and possibly some water friction too, but probably mostly air friction. And the formula looks like this again, the law of conservation of energy. This time we have heat. We'll fill in the numbers now and do the calculation. So we get the equation looking like this when you put the numbers in. And don't forget, heat was produced over here. And it looks like this now. And let's just get all the numbers onto the left side of the equation, and the variables stay on the right side. This is what it looks like when I take 5,550 away from each side. So I took it away from this side, and I have to take it away from this side. Now I just have to get that number here, divide it by 32.65, get the root of it, and I've got my answer. And it simplifies down to this little green equation here. And just finishing it up, 17,872 divided by the 32.65 equals 547.38. That's VF squared. So you have to get the root of it to get VF. And that turns out to be 23.4 meters per second. If you multiply that by 3.6, you get 84.2 kilometers per hour, which is sizably less than the 100 kilometers per hour with friction. And that's it. So just finish off the 2 practice questions and email them to me, and have a good week. Bye.